Now let's look into the conditional probability distribution. Conditional probability distribution is a probability distribution that gives the probability of an event set or a set of events occurring. So, given the occurrence of some other event or set of events, it's similar to the conditional probability that we have seen in probability theorem or probability theory section. So the conditional probability distribution is a probability distribution that gives us the probability of an event or a set of events occurring given the occurrence of some other event or some other set of events. That's it. Similar. So in the context of computer vision or computer vision and NLP, that's a natural language processing, conditional probability distribution is used to compute the probability of a particular feature or a word occurring given the occurrence of some other feature or some other word. The word for NLP, the feature is for computer vision. Let's take one example before we see theoretical aspect of it. So this is a conditional probability distribution. So in computer vision CV, suppose we have a joint probability. Obviously there should be a joint probability first. We have a joint probability distribution of two random variables x and y. Again, x represents the pixels intensities intensities, and y represents the object labels. Now the conditional probability distribution of the conditional probability distribution of y given capital X is the probability of y given a particular value of x, and it's computed using using Bayes rule. It's computed using Bayes rule. So that is, let me put it here in an equation form. P of capital Y is equal to any value of small y, and vertical bar capital X is equals to small x, which is equal to P of x is equals to x. P of x is equals to x, and vertical bar, it's y is equals to y multiplied by P of y is equal to y all divided by P of obviously x is equals to x. So the conditional probability distribution of y given capital X gives us the probability of a particular, it tells us probability of a particular object label occurring given a particular pixel intensity, particular pixel intensity. Okay, this is one example from computer vision. Now let's move ahead with our slide. So consider two random variables, capital X and capital Y. They can be discrete or continuous, or both need not of the same type. It could be one discrete and one continuous, or two continuous or two discrete. It's okay. So conditional probability mass function or probability density function. So P of X given Y has occurred is the probability distribution of one random variable X and fixing other random variable Y. That's what it means. I'm repeating this. Conditional probability of X given that Y has occurred is the probability distribution of one random variable capital X fixing other random variable capital Y. So P of capital X given capital Y is equals to any value of Y, or probability of capital Y given that capital X is equals to any value of X, like taking a slice of the joint distribution P of capital X comma capital Y. That's what it happens. So this is what is this for the discrete random variable on top, and on the right side you have a continuous random variable. So this is your X and Y, and as you know, X comma Y, and this is your joint probability distribution. So now what we want is probability of X given that Y is equals to V. That's like it's like slicing this particular piece. It's like taking a slice of the joint distribution. So this is whole joint distribution of P of X comma Y. But when we say probability of X given that Y with a particular value, so Y with particular value is this row. So I want X in this particular row, particular value of Y, and obviously you're going to bring up a slice of the joint distribution. That's what had happened here. The same thing if it is other way. So probability of Y given that X with a particular value, then you're taking up this vertical slice, because you want Y after X has occurred. So that's the reason you have to take X and you have to block that column. Whichever the value of X is there, that column you have to block. So I have blocked the column, and I will take each and every value of entire Y in that column. So I will get all the values of Y. So this one, no, this all the values of Y you will get here, because this is Y. So 1 2 3 4, all the values you will get it here. This is X values, all the values you will get it for this. So here we want probability of Y, small y1, small y2, small y3, small y4, given that the X is only this column. That's the reason you will bring up only one slice of it. Same thing here. Probability of X, x1, small x2, small x3, small x4, small x5, small x6, small x7, small x8, small x9, given that Y value is only this row, only this row. That's how you get the slices of the joint probability distribution. This is for the discrete random variable. But when it comes to the conditional, when it comes to the continuous random variable, it would be slightly different. And this is how that can be represented. So Note a conditional probability mass function or probability density function may also be conditioned on something that is not the value of an RV random variable but some fixed quantity in general. And here you can see for the continuous random variable, in spite of going for the particular value, we will go for the intervals. We'll go for the intervals. And let me see that. We'll go for the intervals. You see that we have first one, this is p of x y is equals to y1 and p of x y is equals to y2. So we have gone for the two intervals between y1 and y2. Same you will do it for opposite way. P of, if you want the conditional probability of y, then you will give the x and x1 to x2. Like if I want to represent here, so for this one x, the y value is only 1. In continuous random variable, the y value would be between y1 to y3 or y4 to y5. Same thing happens with the conditional probability of x. Sorry, this is for the x. For the conditional probability of y, then the x values will be from here. It's a single value. In that case, the x value will become x1 to x5, x1 to x8, or x2 to x5. So same thing here. You can see it's for probability of conditional probability of x, we have taken the value y1 to y because you have to integrate. That's the reason we have taken the limits. So mm, so that's what is your conditional probability distribution. And if you want to see the one more example, if you're not worried about time, so I can explain the one more example so that it would be much clear. So this time I'll take example from NLP. So uh, uh, for NLP, suppose we have a joint probability distribution of two random variables x and y, where x represents the words in a sentence, and y represents the sentiment labels. So the conditional probability distribution of y given x is the probability distribution of y given a particular value of x. So it's computed using a Bayes rule, similar formula, and similar explanation, nothing much. So the conditional probability distribution is a useful tool in both computer vision and NLP for tasks such as the classification, object recognition, and sentiment analysis. By computing conditional probability distribution, we can gain insights into the relationship between different features or variables and how they impact the overall probability distribution. So we can also use the conditional probability distribution to make predictions and classify new data points based on their features or variables.